All right. Hello, everybody. Thank you for attending today's webinar. I'm Cecile Bonifacio from Fischione Instruments, and I'll be talking about our work with NanoElectronic in electronic imaging on specimen preparation for STEM EBIC failure analyses. This webinar is in collaboration with William Hubbard, who will be presenting with me. So before we start, please use the Q&A feature to submit your questions, and we will answer your questions at the end of the presentation. To begin with, we have the outline of the webinar here. Billy will introduce the STEM EBIC technique, and then we'll talk about the experiment details, talking about Fischione Instruments concentrated argon ion beam solution, NEI's two-channel STEM EBIC system, and then we'll discuss our results, and then summarize our webinar. So here, Billy will introduce the STEM EBIC technique.
All right, well, thank you, Cecile, for the introduction, and thank you to everybody for being here. We're excited to share these results with you. So the technique we're going to be talking about today is STEM EBIC, and EBIC stands for electron beam induced current. And it's basically just measuring the current generated in your sample as it's scanned with an electron beam. But depending on how that current is generated, you get imaging contrast related to different electronic features in your device. So for example, if you're familiar with the term EBIC, you're probably thinking of what we call the standard EBIC mode. And this is current generated by the separation of beam-induced electron hole pairs in a local electric field. This type of EBIC has been done since the 1960s and is most often done in the SEM, but we can also do it in the TEM and scanning mode, hence STEM EBIC. So this image to the right shows an example of this type of contrast where we have our EBIC in red overlaid on our annular dark field STEM image. And this bright horizontal feature we see in red across the sample corresponds to the electric field at the PN junction in the silicon photodiode. Based on the sign of that EBIC signal, we can tell the direction of the electric field, which tells us which region's p-doped and which region's n-doped. We can also measure how that signal attenuates as you move away from the depletion region, and this gives us a measure of the minority carrier diffusion length in each of these layers. And so there's a lot of information you can get even in just one image with this technique. But we're actually not going to be talking so much about this type of EBIC today. We're going to be focusing on a much more recently demonstrated mode of EBIC called CBIC. CBIC stands for Secondary Electron Emission EBIC. And in CBIC, you don't need an electric field to generate contrast. Basically, as the beam scans your sample, it ejects some secondary electrons, and CBIC is a measure of the holes left behind by that process. CBIC is typically a much smaller current signal than standard EBIC by about a factor of 1,000. And so this EBIC mode has motivated a lot of the hardware and technique development we've done over the past few years. In the configuration that we're showing in this diagram, we're making one connection to our sample and measuring the current that's generated in our sample from that one terminal. And so in this configuration, your CBIC image is basically going to be similar to a secondary electron image you might get in, say, an SEM or even in the TEM if you install an SE detector in the column. But the difference here is we're not generating our signal by relying on secondary electrons to reach some remote detector. We're actually taking a measure of all the secondaries that leave the sample. And so this allows much more quantitative measure of secondary electron emission. So you can measure things like work function and temperature based on the signal. And it also provides contrast related to both the top and bottom surface of your thin lamella. There are a number of other interesting properties of CBIC, but for what we're going to talk about today, the most important one to note is that CBIC provides the only technique in the TEM that gives us imaging contrast related to electrical conductivity. And these images at the bottom right show a very basic example of how that contrast works. Here we have two platinum electrodes patterned on a silicon nitride membrane, so they're very well isolated from one another. If we connect an EBIC amplifier to the left electrode, like we have in this middle image here, when the beam is on that electrode, we measure that bright, positive hole current from the CBIC. But when the beam is on the opposing electrode, we don't measure those holes in that image. And that's because they're reaching ground through the opposing electrode, which we also have an EBIC amplifier connected to, this kind of red amplifier signal on the right. And so the basic idea is Wherever the beam parks, it deposits a batch of positive test charges. And by making these multiple connections to our device and monitoring the current through each, we can determine the path that those holes take to ground, and this is what gives us our resistance contrast here. So here is an example of using both of those different EBIC modes in the same sample for different purposes. This is a cross-section device extracted from a gallium nitride HEMT. This was prepared with a xenon plasma fib in hopes of reducing the surface leakage here so that we can do some biasing of this device in the microscope. In this low mag STEM EBIC image we see here, most of the contrast we see in the upper third or so of the device is from this CBIC conductivity related contrast. And what it's telling us is that we have good connection all the way down to our gate electrode, but more importantly, that region is isolated from the rest of the device. We see this nice well-defined boundary along this bright region, which happens to sit right at the passivating silicon nitride layer in this device. And what this means is when we bias this device in situ, rather than driving a current across the surface, we're actually changing the potential and the electric field below the gate. And this allows us to do things like map the electric field and the charge density in this gallium nitride HEMT as we bias the gate. And we can even observe the 2D electron gas depletion as we bias the gate and turn the channel off. And so we can obviously get some really interesting results if we have the proper samples in STEM EBIC. And so the question we want to ask is, how do we obtain similar results in a gallium fib? Most of the time, or most of the fibs, especially in the semiconductor industry, are gallium. The plasma fib is a bit rare. And so this brings us to our collaboration with Fischione, where we have the goal of preparing samples with a gallium fib, but using their argon milling system, the pico mill, to clean these samples to make high quality samples for STEM EBIC analysis. And also this secondary electron mode of EBIC is very surface sensitive, and so we can actually use it to assess the quality of these surfaces.
Thank you for that introduction, Billy. So I'll discuss a little bit more about the specimen, the details of the experiment here. So we've looked at two types of advanced semiconductor devices, a 14 nanometer FinFET device where we prepared it in the gallium fib as an inverted configuration. And then we also have a 7 nanometer FinFET device prepared as a conventional TM specimen. Now, the ion milling system that we use a gallium fib and then use the picomill TM specimen preparation system by Fischione to clean all that gallium implantation and amorphous damage from the gallium fib. And then we characterize the samples using NEI's two-channel STEM EBIC system. So to describe more about the two sample types that we have, the 14 nanometer FinFET device was prepared in a regular OmniProbe half grid, and this is where we did the one-channel STEM EBIC. And then we have, for the two-channel STEM EBIC, we used the NEI silicon-based biasing device where we have all the contacts here, as you can see in the SEM image. And then here is a zoom up image where the lamella is connected to the bottom and top electrodes, which is colored here. So for the FIB preparation, so you start to prepare the samples just like up to the J-cut or the U-cut step in the conventional TM's preparation. Before you lift out the specimen, it's very important that you rotate the stage at minus 15 degrees and then you insert the easy lift or lift out needle in this case. One thing to note is that it's very important to put this needle more on the edge of the specimen. This will prevent any kind of contact with the needle and into the biasing chip as you try to weld it on, you weld the sample onto the device. So here, after you lift out the system, lift out the specimen, you try to go to the NEI device. And then here's just showing you how to approach the specimen with respect to the device. And in this case, we rotate the stage at minus 15 degrees, as you can see in this schematic. And then from there, by looking both the electron beam and the ion beam, you want to approach the NEI device here slowly, and then you basically just welding one side, which is the right side here. So again, this perspective is the electron beam perspective here. So once you weld the right side of the device, you can now cut the needle free from the sample. And then the next step is to first rotate the stage at plus 15 degrees so that you can weld the left side of the device. So these are the different steps that you have to do for preparation of the specimen on the biasing chip device. So one thing to note is also when you're welding, we're welding the specimen, you want to make sure that all the edges of the specimen has platinum deposition so that you're sure that you're contacting good contact on the NEI device. So another thing that's different with this preparation is performing isolation cuts. So you basically polish your sample down in the gallium fib up when you reach about 900 nanometers to about 1 micron. This is when you want to do the isolation cuts. So the isolation cuts is it's dependent on what you want to isolate in your device. So in our case, we want to isolate the silicon substrate and then the metal line here. So depending on what you want to look at for FA, this is where it becomes important to do the STEM EBIC. So in our case, what we've done here is that we tried performing isolation cuts at the gate level, which is shown here on the left, and also above the metal line 4, as you can see here. So we're trying to see that conductivity watershed that Billy described. So after preparing the samples in the fib, we use the picomill system. This is the Fischione instruments ion milling system where we have inert argon gas, and the system has ultra low energies. So we're talking about 2 kV and below, and the beam size of the argon is 600 nanometer. This system has an integrated electron column, so basically an SEM, and have multiple detector systems for imaging. And in this case, you're able to target only the specimen by applying the milling box. And I'll show that in the next slide here. So the animation shows you how the electron beam actually moves within this user-defined milling box. So in this case, you're only targeting the specimen or the lamella that's welded on in this case, it's a half grid. So this is the ion imaging at 300 EV. So we're using the secondary electrons in the system, and that's how we visualize it. And because we have an electron beam column, we actually can do in situ imaging as you're milling. So how does it look like inside the picomill system? So actually the specimen sits on a single tilt TM holder. So that's what it's shown here. And the ion source is stationary, and the TM holder tilts within the range of -15 and 25 degrees, specifically for the samples that we prepared here for this webinar.
All right, and so all of the EBIC data you're going to be seeing here was acquired on our 2-channel STEM EBIC system, which is compatible with most major brands of TEMs with scanning mode. And in the system, everything from the substrates to the holder to obviously all the electronics are specifically designed for the sub-picoamp sensitivity that you need to measure this EBIC mode. Typically, EBIC systems are designed for the nanoamp currents that you see in the SEM, for example. And so you really need to dial in that sensitivity to see a lot of the contrast we're going to be looking at today. This system's equipped with 2 independent EBIC channels. We can measure EBIC from 2 different device regions simultaneously, and we'll see several examples of that coming up. It's also compatible with biasing and heating experiments, like the gallium nitride results I showed earlier. And if you don't have a TEM, we also offer STEM EBIC characterization as a service. So if you would like to try something like this on your samples, that's also a capability. Okay, so now we're going to get into some data, and we're going to start with the single channel STEM EBIC measurements. And just to remind you that the contrast in this mode is very similar to secondary electron contrast you would get with normal SE or SE in STEM imaging. And so we're sensitive to things like the work function, to some degree conductivity, and also surface topography. And so the STEM EBIC image here of a device that was prepared with gallium fib only, so no post fib cleaning, um, you can see there's kind of this kind of grainy, fuzzy residue across the surface. You can see the fins, but they're not very well defined, and you have some kind of lines of residue across them. And so just to the eye here, it seems like this surface is a bit contaminated. And so now let's take a look at a sample that we've argon milled with the picomill system. And just very clearly, you can see this is a much better quality surface. You have a much better, it's much more well-defined signal between the SiO2 and the silicon fins themselves, and we no longer have these little globs along the surface. We can also be a little more quantitative about this and take a line profile across these devices. And you can see the clean sample in black. We get just much sharper contrast features, much bigger difference between the fins and the material surrounding them. With this red profile before cleaning, everything's a little bit more kind of condensed and not so dynamic in terms of the contrast. I also want to point out here that all of the contrast we're seeing here, note that this current scale is in picoamps. Everything we're seeing here happens within a 400 femtoamp scale. And the features that we're looking at are occurring on the order of tens of femtoamp. And so this really underscores the need for very, very sensitive current measurements to see these secondary electron EBIC modes. So we can also do some EDS on these devices in order to confirm that what we've removed here is in fact gallium. And so again, the gallium fib prepared sample is in red, the argon milled sample is in black. You can see, especially at this gallium L-edge peak, is completely gone in this black curve here. So basically those specks we were seeing on the surface are from conductive gallium residue. All right, so now we're going to move on to the two-channel measurements, and these are again secondary electron contrast, but in this case we're seeing more of this differential contrast between where we're better connected to one device terminal or the other. And so at the bottom right, we can see the two simultaneously acquired EBIC images, where we see this bright contrast kind of creeping up from the substrate layer and down from the metallization layer. And at the top right, we have this overlay in green and magenta, where you can see this dividing line between where we're better connected to one device terminal and the other, which in this case happens about halfway up the metallization layer, approximately where we make this isolating cut. And so we have some really interesting contrasts in the device layer. If we zoom in, we can see that in the ADF stem, we don't really see too much in terms of distinct features from fin to fin. There is some curtaining here, but aside from that, there's doesn't seem to be any special about any particular fin. But in the STEM EBIC, we see these very clear gaps in the signal where we're seeing regions that aren't contributing to this conductivity network here. And if we overlay them, we see that there's some distinct individual fins, like on the left, a couple pairs of fins on the right, and even a trio of fins in the middle. And so what we think is happening here is there are certain fins that are do not contribute to signal processing, but they're left in place in order to maintain mechanical stability as you're making these arrays of fins. So these are called dummy fins. They're not doped properly or connected to properly to make good transistors for signal processing, but they're still left in place. And so what we think we're seeing here is the active fins in green and the dummy fins in, I guess, grayscale in this case. And so if we zoom in on this trio of fins, we can see that the boundary between the active and inactive regions is happening over just a few nanometers. And so we get this very, very high resolution electronic contrast related to the presence of dopants in these areas, which I believe is entirely unique among other TEM-based imaging contrast. And so you also might notice that there's still some residue on the surface. Remember that this device was not cleaned with argon milling. We just did gallium fib prep on here. And so we'd like to see what happens when we clean this surface, and we can hopefully make this boundary a little more well-defined. And this gives us a more precise measure of, for example, the diffusion of the dopants between the doped and undoped regions in this case.
So here are the results after argon ion milling. So in this case, we made the isolation cut much lower near the gate level, metal zero in this case. And just like what Billy showed in the STEM EBIC in the substrate, you get high intensity here. And then unfortunately, this device actually cracked here. So you could see that it's mostly connected to the substrate. But before we get into the details of the STEM EBIC, I want to show that by using the picomill, you can actually control the removal of material or the specimen thickness reduction. So if you look after gallium film milling by ADF STEM, you have high intensity contrast on the metal lines. But after picomilling, you start to see that the change in contrast is much darker contrast, indicating specimen thinning. So if you look at metal 5 years really bright, and then after picomilling it start to get the darker contrast in this case. So it's the whole specimen itself is thinning. Now if you look at again the STEM EBIC data, so like I mentioned before, this lamella is well connected to the substrate, and so you can see here it is very bright, high intensity here. And then if we overlay, we colorize it on the ADF stem, you see some very interesting features that if you zoom in here, what we actually see is that by the ADF stem, you start to see some missing fins. So this is actually, they call this silicon stringers, and this is from the fabrication of the fins. This is actually as expected. However, when you look at the STEM EBIC data, you start to see some of the fins through the thickness of the specimen. So meaning there's actually active fins behind the silicon stringers. So this is just shows you how STEM EBIC is very sensitive to actually specimen thickness. You can get a lot of information.
All right, and so in this last portion here, I'll talk a little bit about kind of how STEM EBIC fits into kind of failure analysis. But I want to start by saying that the contrast that we're seeing here with kind of the active and inactive fins is really interesting, but it was a bit surprising. We actually weren't initially trying to look at that type of EBIC in these devices. Next slide, please. There we go. We were actually trying to look at the electric field, the standard EBIC contrast at the dopant interfaces in the device layer. But the reason why we're not seeing it in these samples is if, for example, you look at this kind of green magenta image here that I showed earlier, the dividing line between where we're better connected to one terminal or the other is happening kind of up in the middle of the metallization layers. And so if you can imagine generating and then separating an electron hole pair at the device layer, you might be able to locally separate those pairs, but by the time they reach the EBIC amplifier, they'll have recombined. You'll measure no net current. And so this middle diagram on the right is kind of a cartoon of what we have now. What we would like to do is move this dividing line down so that it basically sits right at the device layer. And so if we separate an electron in a hole, the electron will go up, the hole will go down, and we'll see this electric field contrast. There's a couple knobs we have to play with here. One is that we can change the position of this isolation cut, which Cecile talked about earlier. But another one is just to make sure we have a very clean surface, and so we can kind of reduce the amount of recombination we have on the silicon side of the device. And we were initially going to start wrapping things up here. However, just a few days ago, we actually got lucky with the device. And so we're showing you some data that we've not showed anywhere else. So you guys are lucky enough to get a preview here. We are still working to understand exactly what's going on here, but it's a good example of this dopant-related electric field contrast. So one major difference about this device is that it was extracted with fib and then rotated so that we're thinning from the silicon side. And this prevents any redeposition of either the metal capping layer or the metallization layers from contaminating the silicon side of the device. There's some interesting features in this colorized EBIC image, but the main point here is that if you look in the middle, we have this scenario here where we have our substrate and our metallization layer, that watershed, that dividing line between them is falling right at the device layer. Another property of this device is that if we do electrical testing and measure the leakage across it, this picomil device is almost 2 orders of magnitude more resistive than the first device we looked at that was prepared with just gallium fib. And so we think a main reason why we're seeing these results here is because we have a much cleaner sample, especially with this inverted prep followed by argon milling. And so if we zoom in on the device layer where we had that kind of nice green and magenta dividing boundary, here we've kind of rotated the field of view. So now we're kind of looking in the normal orientation with the metal up top. In the EBIC measured from the metal, we have this kind of CBIC contrast from all the metal from the secondary electron emission of that metal. But we also have some kind of bright and dark spots mixed in there. Though the opposite sign of those features are more visible in the signal we get from the substrate because we're not measuring the secondary electron signal from those metal layers. What we're seeing here are just these bright and dark spots, which are coming from this electric field-based contrast. And what's interesting is if we colorize this data, where we make positive current red and negative current blue, we see this repeating pattern of a couple bright fins, a darker fin, couple bright fins, dark fin, darker fin. And so we don't believe this is some artifact of our sample prep. We think this is something inherent to the structure of the device region we're looking at here. If we zoom into this individual device on the right, we can see this really well-defined bulb of dark contrast that we measure in the substrate between all these electrodes. It's about 18 nanometers wide at the top there where it meets that short contact. And we can see some structure within it along the edges of it. And so we're not exactly sure what it is, but it seems to be consistent with the contrast we would measure from an NMOS device, where we're measuring the electrons in the n-doped well in the substrate side of the device, and the corresponding hole is going up through the metal contact. And so the point here is that we can see this electric field-based contrast if we have the right sample prep, and we get something approaching nanometer resolution for this type of contrast. There's been some interesting work recently doing similar things in the SEM, but this gives us much higher contrast than that work. And so putting this all together, both this electric field dopant contrast and this conductivity-based dopant contrast are both accessible with STEM EBIC at high resolution on these FinFET devices. And this measurement is much more convenient than doing things like atom probe tomography or conducting AFM, which are kind of the only other methods people typically use for looking at dopants and dopant contrast. And in particular, it's much easier if you're already doing TEM. You just take these images alongside your normal characterization. And it's also non-destructive. You can scan the same region multiple times and get the same result. And so one last thing I want to say is that we're kind of flying blind here in terms of these devices. We just have a commercial processor that Cecile is cutting into and looking for interesting features, and we're seeing kind of what EBIC contrast we get with that. But if you have access to the layouts of these devices, especially if you're in the semiconductor industry, you can take a much more targeted approach to device preparation and get much more interesting contrast that's much easier to interpret. And so with that, I think Cecile's going to wrap things up for us.
Thank you so much, Billy. So to summarize, hopefully we've shown that doing STEM EBIC analyses of specimens using the gallium fib is feasible in combination with post-fib argon ion milling. So with the two specimens that we prepared, 14 nanometer and 7 nanometer FinFET, we've shown that the specimens are free from fib-induced damage, specifically gallium implantation, and then you can get pristine surface quality by post-fib argon milling, and this is revealed by the STEM EBIC technique that we've shown. And we actually improved the electronic quality of the data set that you have by post-fib argon milling. So in fact, this data set actually shows the electrically active and inactive FinFETs, and also the dopant-related field contrast that I think in FA is very important. So with that, we're now opening questions for everybody. So hopefully this has been a good webinar for everyone. So actually, Billy, I already have some questions.
Great.
Okay, so the first one, I think you should answer these. The question is atomic resolution STEM EBIC possible? And if not, what are the limiting factors?
So that's a great question. So we're working with two different EBIC modes, and they each have a different associated interaction volume. So for the secondary electron EBIC mode, secondary electron imaging has been demonstrated at atomic resolution in the TEM, and we have also done CBIC imaging at atomic resolution. And there's also some work out of Oak Ridge National Lab looking at a kind of a van der Waal material. I think it was tungsten diselenide. And so, yeah, for the CBIC, for this conductivity mapping, absolutely can be done at atomic resolution. For the standard EBIC mode, you're not limited by the resolution of your microscope. Your resolution is limited by the minority carrier diffusion length. In a lot of semiconductor materials, that diffusion length can be tens or hundreds of nanometers. And I think for that reason, a lot of people don't typically extend work they can do with SEM EBIC to the TEM. However, as we saw with this device here, we can get this this electric field contrast, approaching nanometer resolution. We've also seen some very sharp boundaries in this type of contrast in gallium nitride and hemp type devices. So it
Mm-hmm.
depends on the device, but for another good example is if you're looking in dielectrics, we've done EBIC looking at dielectric breakdown, for example. And if you're in an insulator and you have an electric field, that can be on the order of nanometers or even less. So it may be possible to get down to atomic resolution with this electric field mode, but that's something we haven't observed yet, and it entirely depends on your carrier diffusion in that sample.
Great. Another question, and this is very relevant to what we're doing. And the question is, how is it possible, how are possible electrostatic discharges prevented on extremely sensitive samples?
That is a question that has plagued many grad students
Yeah.
for many months. Yeah, so you need to be careful. The number one thing is just at every step of handling, you need to make sure. Um, Basically, the process is whenever you're handling the
Mm-hmm.
device, you're using ESD safe tweezers. When you store and transport the device, you need a case that's ESD protected.
Mm-hmm.
And even when you're loading the device into the microscope, you need to make sure that you have all of your terminals grounded through a fairly large resistor so that if you do get discharge, it'll kind of dissipate very slowly. Um,
Mm-hmm.
there's even crazier things like there's certain rooms where if you load a sample, you're more likely for them to explode. So you do need to be
Mm-hmm.
very careful. But we've if you do things right, you can get a pretty close to 100% success rate as far as ESD goes. But
Yes.
and if that's something you're interested in, even if you're not particularly interested in EBIC, feel free to reach out. I've spent years looking at different devices with especially these lower resistance devices can be more troublesome. So if you want some tips, I'd be happy to give some
Mm-hmm.
advice on that.
Yes, and we've been lucky. Like I would send samples to Billy, and some of them are like most of them actually have been pretty good, and we were able to get some data. So yeah, what Billy said, ESD tweezers and the membrane boxes that are conductive already are very important, and handling, of course. So another question, Billy. I'm currently working on the conductivity degradation of some metal materials. Would such materials without any junction be possible to use EBIC?
That's a good question. So yeah, there are some limitations to how low the resistance is for your device. You run into things like Johnson noise, and also there's always going to be a little bit of voltage offset in your amplifiers here. So of course there's going to be some current offset. And so generally, if you're larger than a mega ohm total resistance in your device, that things should be fine. Below that, it starts to get a little sketchy. And so if you're looking at just a metal wire that's a few ohms, that might not work for this conductivity mapping. However, you can put resist with our system. You can put resistors in series to bring down the total circuit resistance, so that if there is maybe some grain boundary electric field at some grain boundaries along that wire, you should be able to still see that contrast. So the answer is maybe, and it really depends on the particulars of the device and the type of signals you're trying to see.
Mm-hmm.
And again, please feel free to reach out to me if you want to discuss
Right.
this in more detail, maybe show the type of samples you're interested in.
So another question is how fast can the STEM EBIC data be acquired, and what are the limitations for the acquisition speed?
So another great question. So the acquisition is entirely limited by the bandwidth of your EBIC amplifier. So when we're measuring these very small sub-picoamp signals, the images are somewhere between 100 and 200 seconds for a 256 by 256 pixel image. If we're looking at larger signals, like those GaN-HEMT measurements I showed earlier, we can operate a bit faster, like 10 or 30 seconds per frame. You can for both of these, you can operate even faster. The issue is you'll still get your qualitative contrast, but if you're trying to be quantitative and do measurements as trying to get real quantitative measurements of the secondary electron emission, especially as you change your device, then you want to operate within the proper bandwidth. But you could probably do 60 seconds or so without losing much image quality for this kind of very high gain sub picoamp imaging.
Mm-hmm. Okay, we have another question specifically on our the newest data that we have. So the
Okay.
question is, was the conclusion that you were able to identify a PN junction with STEM EBIC? So that's the question. And so that the darker regions are NMOS. If so, did you perform compositional analyses to confirm these? So I'm
Okay.
gonna make a comment really quick. So, like Billy said, this is brand new data, and we're still like figuring out what we're seeing here. But what we've done is measure these gate structures here, and then compare it to what's available as far as this is a 12 chip. And so what we found is that this size of the gate oxide here actually matches with an NMOS device for the specific device. As far as compositional analyses, maybe Billy, you can comment on that.
Sure. Yeah. So we haven't done EDS or anything on this. But historically, we see pretty obvious contrast with STEM EBIC in this 100 or 200-second scan we see here. Um, when we're looking at devices like these, we can sit for a half hour with high beam current and see no indication of these dopant atoms. And I'm sure there's better EDS out there and people who have systems capable of doing that. Yeah, but in general, it's much harder to see the dopant contrast in non-electrical measurements like this. The other thing that I'll say is that we here we know that we're seeing this electric field signal, which the only electric field we expect to be in the semiconductor layer is from those dopant interfaces. And the way that we know that this electric field signal is because another advantage of measuring EBIC in two channels is that if we add these two channels together, basically for every electron that we measure in one EBIC amplifier from this electron hole pair separation, we're going to measure the corresponding hole in the other amplifier. So you notice in this middle image that we have bright contrast between these electrodes, and that is the exact same magnitude of current, but opposite sign of the EBIC we see in the other image. And so if we add these together, that signal disappears. And that's how we can definitively distinguish between EBIC that's related to secondary electron emission and EBIC that's related to electric field in this case.
Okay, um, that's all the questions that we have. Again, if you guys have any questions, please reach out to this email address and we'll be happy to answer any questions. And thank you so much for attending our webinar, and I hope you guys have a good day. Thank you.
Oh, yeah, thank you so much.